All right, so today we're going to talk about topological manifolds. And this is the beginning of the subject that will finally get us to what we really want to talk about, which are differentiable manifolds. Now, topological manifolds are actually a fascinating subject, and we know everything we need to know right now to get started with it. And I'm going to begin the conversation with a topological space. And we now know exactly what a topological space is. It is a set with a topology. And I'm not going to be very specific about this topological space, except to say, well, actually, in a way, I guess I am going to be specific, because I'm going to say it has to be Hausdorff, right? It has to be second countable, and it has to have a property called paracompactness. Now, the reason that, well, just as a reminder, Hausdorff, of course, is if there's any 2 points in the space, they can be isolated in their own open sets, and the open sets have no intersection. There's no intersection between those open sets. That's a Hausdorff space. So it has to be Hausdorff. Second countable means that any open subset of our space can be produced by a countable number of a countable basis, so that the basis of this space has to be able to produce all of its open sets with a countable basis. That's very important for our notion of a topological manifold. And the last thing is paracompactness, which is not the same as compactness. It's a little different. And I'm not going to go into what it is, but it is a form of compactness. And to study paracompactness, you have to kind of do the same thing we had to do before. You have to make a cover of the topological space. Turns out, and for paracompactness, you've got to prove that every cover can be broken down into sort of what they call a refinement, which is a cover that's a little bit tighter than the actual cover by breaking these open sets into subsets. And then after you've done that, you're supposed to be able to show that any open set intersects only a finite number of members of this so-called refinement. And it's actually a very interesting subject, but it's a bit subtle. The point is, it's not key to understand the details of what paracompactness is now. I urge you to read about it, and with our understanding of compactness, you shouldn't have any trouble. But the point is these three properties together, these three topological properties, they're all three are topological properties, they ensure that the space is ultimately metrizable. And metrizable means that we can actually create a metric on this space. We can invent a metric that would measure something on this space. And that's what we're ultimately shooting for, right? We're shooting for topological spaces that can be used to model the real world, and we make measurements in the real world. So we need to create a space that's metrizable. And metrizable essentially means that I can take any 2 points in the space, which would be the same as saying any element from the Cartesian product of x with itself, and I can convert that to a real number that's greater than or equal to 0 if it's a positive definite metrizable space. If it's pseudo-Riemannian in a sense, or I guess I should say there is the possibility of making metrizable spaces that are just the real numbers altogether, right? That's very similar to the Riemannian metric and pseudo-Riemannian metric of the vector spaces we talked about before. But in order to be metrizable, which almost always refers to greater than or equal to 0, you have to have these properties, right? And you can almost understand why. The Hausdorff, you have to be able to distinguish points from one another in a very aggressive way, and Hausdorff lets you do that. And compactness and second countability show you that the open sets are under some kind of control, and this makes the space useful for most work. The problem is the vast majority of topological spaces that exist in the world don't have these properties. So right away, not every topological space is even close to being eligible to being a topological manifold, because you do have to have these properties before we're going to call it a topological manifold. So that's one thing you need, is this topological manifold. The other thing we're going to need is basically we need access to Euclidean space, Rn. And remember, Rn is R Cartesian product with R Cartesian product with R n times, right? Which basically means it's an ordered pair of real numbers, A, B, C, D, all the way to, there's n of them, right? And so it's an n tuple of real numbers. So we need to map, we're going to be creating maps from the topological manifold to Euclidean space, which is a set of ordered tuples of real numbers, but all it is a set of ordered tuples of real numbers. Rn alone is just a set of ordered n tuples, right? But we are going to do one step more, and we are going to endow it with the so-called usual topology, the usual topology of Rn, which of course are the open balls that we learned about. The open ball, I guess I'll call it the open ball topology, although it's usually called the usual topology. And all the open sets in the topology are going to be made from unions and intersections, finite intersections and unions, arbitrary unions of the open balls that are available in the topology, in the base. So the base of the topology is these open balls. And once you have that, then you actually have Euclidean space as we understand it, which is this sort of, in 3 dimensions, it's got these axes, and you can plot things in it, and you can measure things from one spot to another. It's normal Euclidean space once you assign it the topology, and it is a topological space. So now I have 2 topological spaces, the space in question and Rn. Now, and that's where we begin our thinking about topological manifolds. We actually need a bit more, and I'll show you why in a moment. Because the first thing we now know we can think about, one question we can immediately ask is our space homeomorphic to Rn? Is there a function that's bicontinuous, 1-to-1, on 2, and it's bicontinuous in both directions, the inverse function and the function are continuous, and continuity in this case means exactly what we talked about in our previous lesson. It has to do with the nature of this topology and this topology. It's very sensitive, as we saw, to the topologies. So this topology has to be rich enough, and this topology is already pretty rich, relatively speaking, compared to some. And we certainly, when we investigated the line interval, we saw all of these much coarser topologies than the standard topology. This topology has to be fine enough that all of these functions, or that these 2 functions, f and f inverse, are continuous. But once they're bicontinuous, 1-to-1 and on 2, then we have a homeomorphism. And the first question I'm going to ask is this topological space homeomorphic to Euclidean space? And Euclidean space is unbounded and infinite and everything like that. Another way of asking that question is, are all the topological properties of this space the same as Euclidean space? So first of all, if it is a homeomorphism, you're kind of done. You just execute this homeomorphism on this space, you do all your work in Euclidean space, and then you convert back if you want, or you just study this Euclidean space, because studying Euclidean space is essentially the same thing as studying this topological space if they are homeomorphic. Because remember, homeomorphisms, they just take the open sets from here and map them to open sets in Rn, right? And likewise, both ways. It maps open balls in Rn or open sets in Rn to open sets in the manifold. So it's just essentially a deformation of the open sets from one to another. So spaces that are homeomorphic to Euclidean space, they're interesting. They're certainly interesting, but they're not the whole story. And in fact, those would be, by the way, topological manifolds, as you'll see when we define it. But that's really not what we're interested in doing. We're interested in doing something far more complicated that still exploits the simplicity of Euclidean space, but doesn't demand the extreme, in order to exploit that simplicity, you don't demand the extreme state where this space is entirely homeomorphic to Euclidean space. We're going to actually look for something else, something weaker, but more interesting, called locally Euclidean. Euclidean, right? We want to find spaces that are not homeomorphic, necessarily homeomorphic to Euclidean space, but some spaces that are locally Euclidean, which means they're locally homeomorphic to Euclidean space. So let's have a look at what that actually means. So the way I'm going to start this is I'm going to consider again some space in question, x, tx, and I'm going to consider an open set in xtx. And then I'm going to consider a copy of, and just for simplicity, I'm going to use R2, right? Not Rn, just R2. And under the normal topology, T, R2, like that. And I'm going to talk about for a moment this particular open set. Let me give it a name. I'll give it a point first. I'll call the point P, and I'll give the open set a name U of P. So U of P is a neighborhood of P. It's an element of the topology because it's an open set, and by definition, that's what an open set is. An open set is a member of the topology, and because it's a member of the topology, it has all those properties we talked about in the past, about unions and intersections and things like that. But this is called an open neighborhood of P, as a reminder. So we have an open neighborhood of P. It's an open set in X. Now, what's important is that this is a topological space, meaning it's a set with a topology. It turns out that UP is also a topological space, and it's important to understand why. If I take all the elements of the topology that are contained inside UP, it turns out that all of their unions and all of their intersections will also be contained inside UP. And the union of all of them will actually equal UP. And then the null set we can throw in there. And suddenly UP is its own topological space. The set is UP, and the topology is the same as the topology of X restricted to UP. And so UP, every open neighborhood of the point P, or likely any other point, for example Q, they are their own topological spaces. UQ, T, X restricted to UQ. So every open neighborhood of every point is always going to be its own topological space, right? And the reason that that is important is because, well, first of all, it's also true over here in Euclidean space, right? Whoops. I'm going to try to stick with dotted lines for these open sets, right? But in Euclidean space, right, this is Euclidean space, here is a open set in R2, you know, with its own point R, and I'll call it, instead of U, I'll call it, say, SR. Likewise, SR with the topology of R squared restricted to SR, that's a topological space also, right? So these open sets here are topological spaces, and these open sets here are topological spaces. And this opens up an important possibility. Now I can talk about continuous functions from this open set to, say, some open set here, and I can talk about homeomorphisms, I'll call it FP and FP inverse, that are one-to-one, on-to, and bicontinuous. And now I'm talking about a homeomorphism, which is, remember, a map from one topological space to another topological space, but that's what we got. We got a map from this topological space, which has, by the way, the subspace topology. I think I mentioned that in a previous lecture. Right? All of these will inherit the subspace topology. Another way to say it is this topological space here, UP has inherited its topology from the superspace. So X is the superspace, UP is the subspace, and it inherits the topology. It's got the subspace topology. So once I do that, I can think of a homeomorphism from just this neighborhood to this neighborhood, and I can talk about a homeomorphism like that, if it exists. So Now my question is that neighborhood homeomorphic to a neighborhood in R2? Now I'm not asking if it's homeomorphic to the whole space, the whole Euclidean space R2. I just want to know if there's a neighborhood in R2, if there's a open set in R2 which is homeomorphic to that open set. Can I find a function bicontinuous one-to-one and onto that it makes it a homomorphism? Because remember, the homeomorphism just depends on the existence of such a function. Well, if I can do it for UP, then my question is, all right, well, what about UQ? What about UQ? Could I do it for UQ? And let's do that one in blue, right? Let's do it in green, I guess. Let's put it down here. Can I find this homeomorphism? FQ, wow, that's a bright green, isn't it? FQ minus 1, 1-to-1, and on 2. Can I take the neighborhood of Q and find its homeomorphism to some point over here? And actually, this point over here, I'm going back to black. That point, the point is f of q, right? That's the name of this point. So in this case, we might think of r is actually f of p. So the point is f of q, and the neighborhood, the equivalent neighborhood would be f of uq, and that's actually fq of uq. This is fq of uq, because now I have to name my homeomorphisms, right? I have to associate the homeomorphism with the actual neighborhood, and the neighborhood's associated with the point. So there's going to be multiple homeomorphisms, so I need a new label, right? So I label it by the point. So in this case up here, I need to write f of p, and then this region, SR, equals f of p of u of p, right? So now I've done this for 2 points. Here's the point, so to speak. If I can do it for any point, and every point in X, if I can find a homeomorphism from a neighborhood of every point in X, so P's accounted for and Q's accounted for, but also all of the points inside UP. Because remember, what's the definition of an open set? It's at least one of the definitions of an open set is a neighborhood of every point contained in the set, right? That's logic that helps you understand why open sets don't usually contain their boundaries, without some bizarre exceptions. But it contains a neighborhood of every one of its points. So all the points there are accounted for, all the points in there are accounted for, and presumably I can build this up. I can build this up for other points, Q, T. Then I can maybe take point L. And notice these things can overlap. There's really no problem with them overlapping. In fact, we're going to discover that those overlaps are critical. And they have to overlap because ultimately I want to account for every single point. So I have to create a cover, an open cover of X. So the open cover guarantees that it contains every point. And then I have to verify that every one of those open sets has a mapping that can take it to an open set of R squared. Of R2 with the usual topology. Now, one thing I need to be a little bit careful here, and I screwed this up in a previous attempt at this lecture, so I don't want to screw it up now. This mapping goes to this set here in R2. This mapping goes to a set, but it's really going to a set in a different R2, right? We're not mapping into the same space over here. Each one of these mappings is from a unique topological space to a unique topological space. So this one goes, so that topological space goes to this topological space goes to this topological space here, which is actually in a whole different copy of R2, right? Right. And the topological spaces that are being mapped is this open set, this neighborhood. The neighborhood's being mapped to this neighborhood. It just so happens this neighborhood is embedded in another topological space altogether. But this is the relevant topological space for the mapping, right? And ultimately, what does this mapping give you? The mapping gives you, for this point P, it gives you coordinates. coordinates. And why does it give you coordinates? Well, it gives you coordinates because of the definition of R2. The definition of R2 is an ordered pair of points, A, B, because R2 really means the real numbers, Cartesian product with the real numbers, which is the set of all ordered pairs, A and B, right? So I've gotten to point P, and I've given it coordinates by this mapping, right? This mapping here gives it coordinates. And that's really where this is going. We are now applying coordinates to every one of these points through this mapping. But remember, each one of these goes to a different version of R2. So for example, it would make no sense for me to say, well, this one maps to a set that intersects this set, because it doesn't. It's going to a different plane altogether, right? It's a totally different mapping altogether. So every one of these F's that come out of here, F of Q, F of T, they're all going to different Cartesian planes. They're all going to different copies of R2. All right? That's sort of an important way of looking at it, I think. Likewise, I mean, if you likewise when it goes backwards, right? When it goes backwards, it's each one of these maps going backwards. It's going to a different. It's landing in a different topological space. Each different topological space having its own name. Now, some of these topological spaces share points, right? And that is going to complicate things, and we'll see why. Probably not this lecture, but the next lecture. Okay, so far, what have we done? We've created a cover of neighborhoods that cover all the points of our topological space, and we've shown that every one of those neighborhoods has a mapping to R2 that is homeomorphic. Every one of these mappings is homeomorphic, 1-to-1 on 2, every single one. And every single one is homeomorphic. So, if I can do that, if I can completely cover X, and every mapping that covers it is homeomorphic to Rn, some version of Rn, which in this case is 2, then I have shown that the space X is locally Euclidean. It's locally Euclidean. And that is the first step to being a topological manifold. Well, that's a step, I guess. The other thing, it has to be Hausdorff, second countable, and paracompact. Okay, so now let me work through this a little bit with an example that'll help illustrate some of this. And the first example will be a little abstract, and then I'll zero in and try to be a little more specific. But the example that is always cited, 100% of the time, everybody does this one, is the sphere. And I'm going to consider a sphere just floating out there in space. The set that I'm interested in is the points on the surface of the sphere. So it's the surface of a sphere, and it has a topology that's inherited from R3 onto the sphere itself. So what does this mean? So first of all, the topological space I'm interested in is the surface of the sphere. Just the surface, not the interior, nothing on the exterior. But I also need, in order to be a topological space, that sphere needs a topology. Well, what topology is it going to use? Well, the topology it's going to use is the topology inherited from R3, which R3 is, its topology is constructed from a basis of open balls, right? All of these little spherical balls that float out in space that can be positioned at any point in space and have arbitrary radii, contain their interior but not their boundary. All of those open balls exist out there. Every open ball, some of them will intersect the sphere and create these little disks on the surface of the sphere, sort of these arced bent disks. And every possible arced bent disk is going to be part of the basis for the topology of the sphere. And so you're basically taking little circles on the sphere, big circles on the sphere. The whole sphere itself is, because you can think about an open ball in R3 that contains the entire sphere. In that case, the entire sphere itself must be part of the topology, because that's that intersection. And this sphere doesn't intersect at all, so that's the null set. So the null set has to be in the inherited topology. And then the rest of them will always be these little disk-like things on the surface of the sphere. That is the inherited topology from R3 on the surface of the sphere. And how do we precisely define the surface of the sphere? Well, you could imagine just taking an open ball, right, that perfectly matches this, right? Say that open ball was S. Then you take the closure of S, that will actually capture the surface of the sphere, because the surface of the sphere, the open ball doesn't contain those points, but its closure does, because those points are all limit points, and that's what the closure is. The closure is a set plus all of its limit points. And then you subtract the so-called interior of the sphere, and the only thing that's going to be left is the boundary. All right, so anyway, so that's the set that we're interested in, is this sphere. Let me erase these little open sets here. And once we have the surface of the sphere, now we're going to talk about, well, can I take, say, this open set, this open neighborhood of that point on the sphere, and can I map it to R2? I'm going to choose R2. And if I did, what would that map look like? Where would it land? It would land something like that. You know, and here's the mapping. I'll call that point P, and here's f of P, and f inverse of P. Now, the first reason that this is such a good example is there's one important thing about the sphere and the plane that you've got to understand. First of all, the sphere is compact. And I'll let you think about this, but imagine any open cover you can of the sphere. And no matter how you create any open cover of the sphere, you will realize that there is a finite subcover of the sphere. So the sphere is compact. But the plane, when you look at it, I can think of a lot of open covers of the plane that have no finite subcovers. And my favorite is the near tiling, where you have these open rectangles, say, that just overlap a little bit, but cover the entire plane. No matter how you cut that, you got to do an infinite number of them, and there's no finite number of them that cover the entire plane. Therefore, I have found a cover of the entire plane that has no finite subcover. Therefore, R2 is not compact. The sphere, however, is compact. So right away, you know one really, really important thing. Compactness is a topological property. This is compact. This is non-compact. Therefore, there is no homeomorphism between the sphere and the plane. So the sphere can never be homeomorphic to the plane. For that one reason alone, there's no function that will ever take the sphere to the plane, because the sphere is compact, the plane is non-compact. That's a topological property, and if there was a homeomorphism, if a homeomorphism did exist, then the plane would have to either be compact or the sphere would have to be non-compact. What's interesting, and it's very important in our next part of this talk, is if I take one point out of the sphere, just one point, right? So I have the whole sphere except the south pole. All of a sudden, the sphere becomes non-compact. And sure enough, all of a sudden, there is a homeomorphism. And in fact, the sphere missing that point is homeomorphism to the plane. Very, very interesting. Why is the sphere non-compact when you take away that point? Well, now you can imagine an open cover, right? I can find an open cover where I create smaller and smaller little open sets around this point, but I never include that point, and I have this infinite limiting process getting me there. And that will cover the entire sphere, and it leaves out that point, but there's no finite subcover. So if I take out one point on the sphere, it loses its compactness. And now, of course, the idea is with that one point missing, I can sort of jam a knife in there and stretch the sphere out and spread it out all the way across the infinite plane, and I can actually make it homeomorphic to the infinite plane. Okay, so the point being that, on the other hand, every open set on the sphere, I can still map to an open set of R2. I can take that one there, I can pick this one here, and give it a map, right? If I call, say, a point in there just to label it T, I can find a map FT, F inverse of T, and then here's another copy of R2, and it maps to this, say, open set in R2, so that's F of UT, right, in here, and then that's FT of T, right here, that point. And I can do that for every single open set on the sphere. So and let me also restore the point that I took out. So even though the sphere, with that point restored, is compact, and the plane is non-compact, it's still true that each region of the sphere, every single region of the sphere that's open, can be mapped to R2, with the exception of the entire sphere. Right? The entire sphere is open, by the way, because it's always going to be a member of the topology. But that one I can't map to R2, because if I could, then it would be a homeomorphism of the total sphere. The distinction might be that the total set of the sphere is more than just open, it's clopen, right? It's also closed. So the fact that it's closed and open could very well be the distinction that prevents it from being mapped. That is the distinction between it and all the other open sets, which are capable of being mapped to some region of the plane. Now remember, when I talk about the mapping, I keep saying, using the language, I'm mapping this open set to the plane, but I'm not. I'm mapping it to a region of the plane, and the reality is I'm mapping it to a topological space that in its own right happens to be an open set of R2. So the mapping is not between the sphere and R2, it's between the topological space, open neighborhood of a point P with the subspace topology to a topological space, which is an open neighborhood of R2 with its subspace topology, right? Likewise, a topological space, which is a subset of a different R2 with the subspace topology. So the point being is that despite the fact this whole thing is not mappable to R2, each region is. And that is what is characteristic of a topological manifold. Every spot is locally homeomorphic to a subset of Euclidean space. And that's what a topological manifold is. So now let's work this example a little bit further and in fact do a bit of a demonstration. So let's sort of take a look at the sphere, and this time I'm going to look at the sphere just edge on, right? So I'm actually only looking at a circle right now, but imagine we're looking at the sphere, and here's the equator of the sphere. Right, so we're looking at it straight edge on. And what I'm going to do is I'm going to look for a neighborhood of, say, the North Pole. Well, here's a neighborhood of the North Pole. Imagine I took the entire, I need an open set that contains the North Pole, and that's a neighborhood of the North Pole, right? So any open set, so this one here would work, that one would work, the upper hemisphere would work, right? The upper hemisphere is an open set if it's not including the boundary, because remember, the open sets on the surface don't include the boundary. But I could even go beyond that. I could go down here. I could take an open set that, well, first of all, I could take, say, this open set, right, that goes around the top of the sphere. I could take this open set that goes around the sphere like that and covers the top part of the sphere, right? So all of these points are in it. That's a neighborhood of that point, right? It's an open set on the sphere, and it contains that point. So that'll work. I could, like I said, I could take the whole hemisphere, but I could keep going, right? I could take this, right, and all of the points above that, so the entire top of the sphere except for this bottom section, this sort of Antarctica type section, everything is in there. That's a neighborhood of that point. It's an open set that contains that point. It has most of the sphere in it, so it's a pretty big open set. And obviously I can keep doing this until I get all the way to the South Pole, and And the biggest open set I can find that contains that point is the entire sphere minus the south pole, that same point that I talked about last time. So that's what I'm going to do. I'm going to choose P as this point here, and U of P is going to be the entire sphere, which is X minus, I'll call this Q, X minus Q, right? That's going to be my open set. So let me redraw this sphere now, because I've got all those lines, and I'm going to redraw it like that. There's the point P. I'm going to eliminate the point Q, right? So Q is gone from this set. And now there's my equator right there. And that is the open set UP. So then, so what I need to do now is I need to find a map for this open set. I need to find a map from this to R2. So the way I'm going to do this is by construction. I'm going to cut the sphere with R2 like that. So now we're looking at the sphere edge on, and this line here is the whole plane R2. And I'm going to now begin to produce my mapping. And the way I'm going to do this is I'm going to start at Q, start at this missing point, and I'm going to take a line and I'm going to draw it through every point in the sphere. So I'm going to draw a line to there, to there, to there, to there, to there, to there, to there. And wherever it cuts the plane, that's my map. That's the mapped point. The coordinates on the plane of the point that the line that connects all these spherical points intersects, that's going to be the mapping. So, for example, let's do the obvious one first. I go right up to the North Pole. Well, that is the mapping point of the North Pole. That is going to be F P of the point P. Then let's take a look at this point here. I'm going to draw a map to there. Well, that so happens that the point is actually on the plane, right? So that point will map to this point. Then I'm going to take this point here, and I'm going to draw this line. And that point maps to that point. And obviously you can kind of tell that every point in the northern hemisphere of the sphere is going to map into the interior circle of the sphere. So now you got to kind of zoom out and spin this thing around and understand it's going to happen in 3 dimensions, right? But we're just doing a cross-sectional view. But likewise, but I can still do the lower points too. Let me change this to a softer color. So this point here, for example, this point here, I can map like that. And this point here, I can map like that. I'm doing a geometric construction of a map, but you can imagine a point really close to the North Pole, right? It's going to map something like that to there, right? So this point maps here, that point on the sphere maps here, that point on the sphere maps here, this point on the sphere maps here, that point maps to itself, this point maps to itself, this point maps here, the center maps to the middle. So I can map every point on the sphere using this technique. Now this is a geometrical construction, but I think you could see that you could very easily calculate the ordered pair of these points, right? Each of these points is going to have, if you look at this from the top, right? If you looked at this from the top, you'd see the sphere sort of sitting here with the North Pole, and you would see, you know, you might draft a little coordinate system for yourself on the plane, and then using some algebra, you could calculate the coordinates of every one of these points. This could be y, and this could be x. And every point on the sphere will map to a point on the plane. And the points in the northern hemisphere will all map in here, and the points in the southern hemisphere will all map out here. But it will cover the whole plane. And it's funny because most of the plane, of course, is covered by the points that are jammed up real close to the pole. But the pole itself, you can't map that, right? You can't draw a line through a single point. You can't map the pole. but you can map everything else, and everything else is this open set, neighborhood of P, so it certainly satisfies this rule. Now we call that map F of P, right? And it's right now it's a technique, but you can understand how it could be algebraic. Then what's interesting is we do this all over again. We repeat this entire process, but this time, and I think you can probably see this coming, we eliminate that point and include that point, and then we draw the same plane through the equator, and now we create a map. Now we call this point Q. We're looking for U of Q, which equals x minus P, right, where P is up here. And now we draw all our lines from P. And we do the same construction. And it's going to result in the same thing, except now the southern hemisphere points are going to be inside the sphere, and the northern hemisphere points are going to be outside the sphere, right? And they're going to map like that. So now I have two neighborhoods. I have U of Q. I have U of P along with its map, F of P. Put those together. And I have U of Q along with its map, F of Q. And those two maps cover the entire sphere. So they cover the sphere, like I said, and there's open sets, cover the sphere, homeomorphic maps. Oh, by the way, I didn't show that these are homeomorphisms, right? So the hard part about being a homeomorphism is got to be reversible. Well, I take a point on the plane, I draw a line to the bottom of the sphere, where it intersects the sphere, that's the reverse mapping. Totally, completely, unequivocally reversible. One-to-one and on-to. So it is a homeomorphism. So now I take these two maps, or I take these two homeomorphisms, pair them up with the set that they're attached to, and put them in a set together. These individually are called charts, and the set that contains all the charts covering the entire topological space in question is called an atlas. Okay, and you can understand why this is a chart. It's a chart because a chart is just a map of a region. It's a map of a region, a map of a region. And when you put a bunch of charts in a book, you get an atlas. So I guess that's how they decided to make that thing go. So this is a perfect example of a topological manifold. Once you rotate it around and realize it's happening in every direction, like when I say you look at it from above, you perform this activity in every possible angle around the origin. So there is your classic manifold, topological manifold, and this is a very nice example because it takes two charts. You can this algebra is actually very easy to work out. It's a little bit of trigonometry, a little bit of algebra. It can be pure algebra also, but you can. I always felt it was easier to do with trigonometry, and it's a really, really good example. It's also a good example of compactness and non-compactness. It's a good example because it shows that the sphere is not homeomorphic to the plane, but locally it is, and that's what matters. That's what makes it a topological manifold, is it is locally, each local region, where local is defined as open sets of neighborhoods of points, is locally homeomorphic to a region or subspace of Euclidean space. All right, so I will do a quick counterexample before we're done here. The counterexample, another classic counterexample, it's done by almost every book on the subject, is a line with another line sort of jutting out. So first of all, this line with this other line, let's just not include these endpoints. So that's sort of these open line. And it's lying there in R2. Again, we always like to embed these things in R2 with the usual topology of R2, because then I can immediately create a topology for this structure. if this structure is considered a line sitting in the plane, in the real plane, the real Euclidean plane, which is the set R2 with the standard topology, then immediately I can get the subspace topology. So any little ball that intersects this structure, the intersection between this structure and these open balls will form a base for the topology of this thing. And this thing, I guess I better give it a name. I'll call it X. But I need to give X a topology. Well, the topology will always be the inherited topology, the topology of R2 restricted to X. So, for example, this little open set would be the result of the inherited topology from, say, that ball. And, you know, this open set here would be from this ball. Likewise, this open set here could be from that ball. The problem, of course, is, well, it shouldn't say a problem, the totally legitimate inherited topological set from that ball is going to be this interesting collection of points that are shaped like this. It's going to be these points, right? In this case, this interval here, this open interval here, is the open set. But in this case, the open set is that open interval and that little thing. All right, so now what am I going to do? If, say, I want to make this thing into a manifold, well, I have to select a Euclidean space. So I'm going to guess, well, how about R1, right? Is this can I make this locally homeomorphic to a line? Well, certainly there's no problem here, right? I can map that to an interval without any trouble. Certainly, likewise, there's no problem here. I could, say, map that to an interval. Obviously, the problem is with this thing. Is there any way of homeomorphically mapping that to the line? And this point here, right, the question is I have to be invertible, right? So if I map that to, say, this region, how do I distinguish this top part from the side parts? And specifically, how do I map, what point on this line can map that point, which is unique? Because remember, that point distinguishes an intersection of three things. So it's sort of unique, but how can I pick out any point on the line that's special in any way? You know, maybe I could try to map this first interval part to this, right? And then I can map this top part to, say, that. That would work, but the problem is that point there, this point, when I blow it up, this point right here, that's in both of those, right? So I guess I could maybe map that point to, say, just its own point, right? Just one point. The problem is one point is not an open set on R1. So that won't work. That will violate continuity almost certainly. And the point is this can't be done. I'm not going to go into it much more, but you cannot create a homeomorphism from that structure, that open set, into the line. So you might say, well, I could maybe R1's not the thing. Maybe I should have tried R2. Well, the problem now is, what about this thing? This thing is homeomorphic to a line segment. But in R2, a line segment is not an open set. So that doesn't work. You can't do that. So it's not R1, not R2, and none of the other spaces are going to work either. So the fact is this structure here simply is not eligible to be a topological manifold. And by the way, most topological manifolds are like this. Not most of the ones that are used in physics, but most of them are actually like this. Okay, so so we have showed a few different things today. We talked about topological manifolds. We talked about topological manifolds. We talked about charts and atlases. Well, charts and an atlas. By the way, this brings up the question of how many different ways of doing this are possible. And it turns out that the intersection of any two atlas, all the sets in the intersection of any two atlases, is also an atlas. And so these things are very, very likely to be equivalent. When we talk about differential manifolds, there is the possibility of having different differential manifolds, a different set of organizing these open sets that make functionally different differential manifolds. Very esoteric subject, but we'll touch on it when we talk about differential manifolds. The one thing we have not talked about is what's called transition functions, and that's where we'll begin next time. But the point about transition functions, which is really, I'll just give you a little taste, is when you well, consider the surface of that sphere that we were mapping, right? Well, we just mapped a sphere. Notice UQ intersection UP was the entire sphere with each of these sets only contained one point that the other set didn't contain. So every point on the sphere is actually in both UQ and UP, with the exception of the north and south pole, which is in only one or the other. Because of this intersection, I could map it I could map any point with FQ or with FP. And so now the question is I land in one open set of R2 with one mapping, and I land in a different R2 in a different open set. These spaces are topological spaces. Well, the question is, well, what's the relationship between them? What's the relationship between these two topological spaces? And the transition functions are these functions here, and they are also going to be homeomorphisms. Right? They're also going to be homeomorphisms. And they're very, very critical to understanding differential manifolds and the value of this entire program. And we'll talk about that next time.